Now in this example, we're asked to find the general solution for the differential equation formed by x prime equals a with our coefficient matrix x. Now our matrix A is given here. As we have 4 rows and 4 columns, we know that this is shorthand for x sub 1 prime, x sub 2 prime, x sub 3 prime, x sub 4 prime, that's our x prime, equals the matrix A, which is listed here. Multiplied by the coefficient matrix x1, x2, x3, x4. So that's just a little note on translating this differential equation written out in our matrix form here. Now as we go about solving this, we know the first step to solve for the general solution of this differential equation using our eigenvalue method is to find the matrix A minus lambda I, which, since the identity matrix is just 1 on the main diagonal, 0 elsewhere, we know this will end up just subtracting lambda from each term on the main diagonal, which I've highlighted here. And then we're asked to find the determinant of that, so I'm looking for the determinant. Vertical bars mean determinant of 1 minus lambda, 0, 0, 0, 2, 2 minus lambda, 0, 0, 0, 3, 3 minus lambda, 0, 0, 0, 4, and then 4 minus lambda. And we know we find the determinant for larger matrices using our row or column expansion. And in particular, we'd like to expand along rows or columns that have a lot of zeros. And I think if we look at our first row, that will be the most efficient one. So we're going to take the first entry, first row, first column, and we're going to multiply that by the determinant of the matrix that remains when you imagine canceling out its row and its column. So it's by this matrix. Okay, we need to take that determinant. We'll do that later. Let's continue. Then you pick the next item and you say switch the sign. It was positive, now it's negative. 0 times this determinant. But the nice thing is, even if I wanted to, I could write it down, and I would get 2, 0, 0, 0, 3 minus lambda, 0, 0, 4, 4 minus lambda. But whatever this determinant is, when I multiply it by 0, the whole term goes to 0, so this goes away. Okay, and then we go along the next item, which for us would be 0 again, and you see the same thing's going to keep happening. We're going to say 0 times whatever this determinant is. Anything times 0 is 0. And then we move to the next item. Here's our 0. Minus 0 times whatever this determinant is. But again, 0 times anything is 0. So if we expand along the first row, because there's a lot of 0 there, it's going to work out particularly nicely. Now, as we find the determinant of this 3 by 3 matrix, we'll do a similar thing. We'll expand along the top of this matrix. Feel free to pause the video and attempt it on your own if you haven't already. And it would be 1 minus lambda, okay, times first item, cancel its row and column, find the determinant of the remaining matrix. And for similar reasons as we just discussed, as we expand along the remaining pieces of this row, they're all zeros, so all the later terms will disappear. So I don't have to keep going through that in this particular case. Now this is a 2 by 2 matrix. We know its determinant is the main diagonal multiplied together minus the off diagonal. And this will give me 1 minus lambda, 2 minus lambda, okay, and then we have our 3 minus lambda multiplied by 4 minus lambda, and then since we're subtracting 0, that's not part of it. And nicely for us, this is already in a factored form, so we can quickly identify that the first eigenvalue should be 1, the second eigenvalue should be 2, the third eigenvalue should be 3, and the fourth eigenvalue should be 4 from our factored form of the determinant of the coefficient matrix. So now all that's left to do is to find their corresponding eigenvectors, and then remember that the general solution is a linear combination of those eigenvectors. So let's write that out. So when lambda 1 equals 1, we are going to substitute 1 for each lambda in our original matrix. And that will give us 1 minus 1 is 0. First row is all 0. 2 minus 1 is 1. 3 minus 1 is 2. 4 minus 1 is 3. And we know to find the eigenvector, we're looking for what coefficients do our A, B, and C need to be such that when we multiply these two matrices, we get the zero matrix. Okay. Now, as we multiply this matrix, we know we imagine taking this up, flipping it 90 degrees, and then we're going to multiply it through the rows. So it's like we multiply our A, B, C, D through this row. 0 times A plus 0 times B plus 0 times C plus 0 times D equals 0 doesn't give us any information. But if we expand this down to our second row, we'll get the equation 2A plus B equals 0. Now we'll take this to our third row. A times 0 is 0, but then we have 3B plus 2C equals 0. Multiply this through by our fourth row, and we get 4C plus 3D equals 0. So we'll work to solve these three linear equations to get correct values of A, B, and C and D for our eigenvector v sub 1. Now we see that I have multiple variables listed here. Let's solve each of these equations to get one of the variables by itself. Here, I'm going to get B by itself. I'll subtract from both sides and we get B equals 2A. Next, we'll get B by itself again. Subtract 2C, divide by 3, and we get B is negative 2/3 C. Finally, let's solve for C. Subtract 3D, divide by 4, and we get C is equal to minus 3/4 D. Now the idea behind this is we have these relationships then about how A, B, C, and D should relate to each other. And we don't have exact values for A, B, and C, and D because it's more of they have to have this ratio. The values A, B, C, and D must fit this pattern. Whatever D is, C is negative 3/4 of that. Whatever C is, B is negative 2/3 of that. Whatever B is, that's equal to 2 times A. So let's pick a value for D. And in order to cancel the fractions nicely, since we can pick any value, we'll pick a nice one. Let's pick D is equal to 4. So if D equals 4, then C should be negative 3/4 times 4, which would give me negative 3. Now that we know C is negative 3, we'll evaluate that into this equation, and we get B then should be negative 2/3 times negative 3. That gets me that B is equal to positive 2. But if B was positive 2, that's 2 times A, that tells me A should be 1. So we found our eigenvector for the eigenvalue of 1. For the eigenvector 1, we should have 1, 2, negative 3, and then 4. Now here I just noticed a quick error. Hopefully y'all already caught it throughout this point. When I solved this equation to get it by itself, I just noticed I subtracted a 2a, so that should have been minus a 2a, which means this should have been a minus 2, which would make this a negative 1. So we do need to make that correction. Now let's similarly solve for the eigenvector when lambda is 2. So when lambda 2 equals 2, we have our matrix 2 everywhere there's a lambda above. 1 minus 2 is negative 1. 2 minus 2 is 0. 3 minus 2 is 1. 4 minus 2 is 2. Now we'll write out our systems of linear equations and then solve for the relationships between a, b, c, and d in order to make the equations equal to 0. So from our matrix multiplication, I get negative a must equal 0. Well, that tells me a must be 0. Next row, I get 2a equals 0. No surprise there, that also gives us a equals 0. The next equation will give me 3b plus c equals 0. Final equation, 4c plus 2d equals 0. Now let's solve this. We can get c by itself and d by itself. When we solve for c, we get c equals negative 3b. And d would be subtract 4c divided by 2. That should give us that d is equal to negative 2c. So we know a must be 0, but then b, c, and d must be related in this way. So for instance, what if we let b equal 1? Then that tells us c must be negative 3 times 1, or negative 3. Okay? Now if c is negative 3, we know that d is negative 2 times negative 3, which is positive 6. So that would give me the eigenvector v sub 2. A is 0, b is 1, c is negative 3, d is positive 6. Now let's continue, repeat the process for our eigenvalue, third eigenvalue, which is equal to 3. Lambda minus 3 is, or 1 minus 3 is negative 2. Okay, we'll multiply and get our system of equations. Negative 2a equals 0, that tells me a must be 0. Down to the next row, 2a minus b equals 0. Well, we know a is 0, so this is 0 minus b equals 0. That means that b also must be 0. Down to the next equation, and we get 3b equals 0, again letting us know b must be 0. Final equation, 4c plus d equals 0. We can solve this and get d by itself. D must be negative 4 times what c is equal to. So we know a and b are 0, d and c are related in this way. So let's pick a nice value for c. If c is equal to 1, this tells us d would be negative 4 times 1, or negative 4. That gives me that my third eigenvector should be 0, 0, 1, negative 4. So let's find our last one. First row getting multiplied by our a, b, c, d column, and we get 3a, negative 3a equals 0. A is then equal to 0. Next we get 2a minus 2b equals 0. Now we know a is 0 already, so this is really negative 2b equals 0. That tells us b also equals 0. Next equation, 3b minus c equals 0. We know b is 0, so this goes away. It's really negative c equals 0. That tells us c is also equal to 0. And our final equation will give us 4c equals 0. Tells us again c equals 0. And we notice none of the equations that came from this matrix multiplication involve d. So there's no relationship upon d, which tells us d can be anything. Since we can pick anything for d, let's pick something nice. We'll go with 1, so we'll say d equals 1. Everything else is 0, so our final eigenvector is 0, 0, 0, 1. So we're almost done with this problem. So in writing the solution, we know that the general solution, if we know the eigenvalues and eigenvectors, would then be some arbitrary constant times our first eigenvector multiplied by e to the lambda t for our first eigenvalue, that's 1, so e to the t, plus some other constant times our second eigenvector, multiplied by e to the, in this case, 2t, plus c3, third eigenvector, multiplied by e to the 3t, plus c4 times our fourth eigenvector, times e to its eigenvalue, which is 4t. And that would be our solution, and this is the solution for just our x in general. If we wanted to write our answer in another way to specify exactly what x1, x2, and x3 would be, we know capital X is representing our x1, x2, x3, x4. So to find what x1 would be, it would be that constant times our first entry times this, plus constant times this times this. Now 0 times anything, that's going to get rid of those terms. And we just get that x1 is equal to negative c1 e to the t. Now to find x2, we do the same thing except for our second rows of the matrices. And we'd end up with these. So either would be an appropriate answer in this case. So this ends our 5.4 notes. If you have any questions from this section or any other section, please reach out. I'll be very happy to help you, and we'll see everybody next week.